morning, everyone, and welcome to our summer live webinar series. Hope you are all doing well and keeping safe. I am Iris Trudy and would like to thank you all for your interest in our webinars. Today will be our first session, which is about lighting basics, and it will be presented by Dia Al-Fasfous. Hi, Dia.
Hi, Iris. How are you?
I'm good. How about you? All good?
All good. Thanks a lot.
So, shall we start?
Yeah. So, thank you, everybody, for attending this series of webinars, which is concentrating on the lighting theory and on the product portfolio that Schroeder offers. We are excited to be with you today. I see today that we have attendances from Bahrain, from Egypt, India, Jordan, Kuwait, Lebanon, Oman, Pakistan, Qatar, Saudi Arabia, and United Arab Emirates. We hope that all of you and your families are safe. We also hope that you will enjoy those webinars and you will find it useful. During the months of July and August, we will have a series of webinars that is focused on the theory of outdoor lighting, like the first session, which is happening today about lighting basics. Then we will have other session in 6th of July where we are speaking about the CIE 140 and 115 norms. Those are the norms or the standard, the international standard, which is concentrating about the recommendation of illuminating outdoor areas like street lighting. Then on 8th of July, we will have the luminaire structure, where we will be focusing about the luminaire as a unit, about the optical compartment, about the component of that optical compartment, and then for the control gear compartment, the component of the gear compartment, the fixation, and what are the certifications required to make sure that those luminaires have quality. We will have also on 27th of July CIE 88 presentation, which is the norm giving the recommendation for illuminating the tunnel. So we will go to understand what is the recommendation to illuminate the tunnel, what is the CIE curve, etc. Then we will have also other series of webinars dedicated for Schroeder portfolio, Schroeder products, starting on 13th of July with air bandico and the brackets. In 15th of July, we will have the industrial portfolio. 22nd, we will have the road portfolio. At 29, we will have the tunnel portfolio. And finally, in August, in 17 and 19, we will have the portfolio targeting the smart cities with OLED and shuffle. Okay, coming to Schroeder. Schroeder is a well-known lighting company that was founded in 1907. So we have almost 113 years of experience. We have presence in 70 different countries with worldwide brand recognition. We are available in the 5 continents. We have more than 2,600 experts in lighting, and we claim that we are the market leader in outdoor lighting worldwide. In 1907, during the first industrial revolution, Schroeder workshop was found. And on 1923, we developed a variety of electronic technologies like the electronic boxes and panel board. So in that time, we were not concentrating on lighting. But in 1933, we have launched our first industrial lighting branch. In 1950, we expanded worldwide. It was the first time that we started expanding outside Belgium. And we started also concentrating on reflector industry. In 1953, we have our first laboratory, and we used it to measure the characteristics of rods. This gave us the flexibility or the flexibility to design our reflector to meet the norms. And then we became, due to that, the pioneer in luminance calculation in the world. In 1970, we have introduced our Z range. which is which marked the beginning of tightness standard for water and dust across the industry, and we have supplied more than 2 million points with the Z range. In 1985, we invented the seal safe system, where we're still using it even in the LED luminaires right now. And in 2012, we have installed more than 22,000 luminaire controllers in San Jose in California, where we are using the radio frequency to control and to monitor the street lighting. And finally, in 2019, Schroeder Hyperion, which is our smart city center of excellence, was found in Lisbon. We have in Schroeder 7 research and development centers and 7 factories. For the research and development centers, we have one in Belgium, one in France, one in Germany, one in Hungary, in Portugal, South Africa, and United Kingdom, while our factories are in China, France, Hungary, Portugal, South Africa, Spain, and Ukraine. Each factory and each research and development center is focusing normally in a specific segment or product range, and some of the products are duplicated in different factories. For instance, we have Ampera that is manufactured in Spain, and in Spain you will find all the road luminaires like Ampera, like TCO, and soon we will have also the EasyLum. However, the same product, Ampera, is manufactured also in China factory, just to serve the countries which is close to China to make savings and to optimize logistics. We need to highlight here that wherever the luminaire is manufactured, is it in Spain, in Ukraine, in China, or even in Hungary, we are using the group sourcing team. So we are using the same component, the same quality, and all the process is identical. So you will not have any differences between the product which is manufactured in China or the product which is manufactured anywhere else, in Spain or in Portugal or in Hungary. Our ambition is to deliver an extraordinary local customer experience, and we are doing that by being involved on the project in the very early stage. We participate in consultation, considering the wide or the vast experience that we have in lighting. We offer also lighting designs for our client, the engineering, the project management. We do supply a high quality products. We are taking advantage of our 7 factory that is distributed worldwide to make sure that we are always coming with reliable delivery proposals. We do technical support, training, and also installation, and we are always available for after-sales services. We also we are open also to any future ideas coming from our clients. In Schroeder, we are active in 5 different segments. The first segment is road, urban and deco, tunnel, industrial, and smart and connected. For every individual or for each of those different segments, we will have a dedicated session. So, for example, if you are looking at the road, we have few products that proved themselves in the previous years. And what you see here are all with LED. This portfolio will be discussed in details on 22nd of July with Isfan and Robert, who will be joining us from the group. Urban and deco for city beautification, also a segment that we are strong in, and we are dedicating a session on 13th of July to explain and to present all the urban deco and the bracket portfolio that we have, the decorative bracket portfolio that we have. And we will take help of our colleague Toon from the group on 13th of July. We are also very well known worldwide on the tunnel segment. We have a portfolio that we will be presenting on 29th of July for tunnel and for tunnel lighting control. Koen van Winkel will be joining us to present this portfolio on 29th of July. Industrial is a new segment that Schroeder is concentrating in. And on 15th of July, Cedric Collard will join us to present the industrial, sport, and large areas portfolio that we have. And finally, the smart and connected portfolio that is targeting smart cities will be presented on 17th and 18th of August. We have two products. We have the smart pole shuffle, where we can integrate lighting and beyond lighting technology. And we have also the OLED, which is our street lighting control product. So, hope that this presentation about lighting basics will not be boring, as it is a purely theoretical part. I tried to simplify it as much as I can by concentrating only about the main terminologies that we are facing usually in our daily work in lighting once we are working on a specification or technical submittals. And we start here. In the next few slides, we will have a short introduction about lighting. Then we will be explaining the color terminologies. And we will also go through the four fundamental photometrical units, which is the luminous flux, luminous intensity, illuminance, and luminance. So, photometry is identified as the science of measurement of light in terms of its perceived brightness to the human eye. We need to understand that the human eye is not equally sensitive to all colors or all wavelengths of the visible light. We will also concentrate, or we will mention on the next slide, small or simplified explanation of the four fundamental units, which is the luminous flux, intensity, illuminance, and luminance. But before that, let's see how vision is happening. To be able to see, we will need three parts. First of all, we need a light source. This light might be natural and might be artificial. Natural like the sunlight, and artificial might be just like street lighting. Then we will need to have objects, where we see here this bus, the yellow bus. This object, of course, it will has a shape and it will has a color. Then we should also have a detector, which is in our case the human eye. So if we are looking here, what we are doing in this presentation, we are just speaking about this part, which is the light. And if I ask anybody, what is the color of the light coming from the sun? We might have an answer. It is white or yellowish white or bluish white, depending about the time of the day. But we need to understand that there is nothing called white color. White color is not an independent color, but it is defined as a complex mixture of other colors or other wavelengths. And all of those colors which is mixed, or I mean, when we are mixing those colors from the visible spectrum, we will receive, or we will have a white light. And the proof of that, if we brought the sunlight and we will allow it to pass through a prism, we will be able to see the components of the light. Normally, if it is high quality light, we will see all the 7 rainbow colors. And if it is different light source, which does not have a specific component, we will not see it. The white color can be, or we can get this white color by as simple as mixing 2 different colors, or we can mix the 7 colors together. And of course, in both cases, we might have the same appearance on the color of the light. However, the quality of objects under those 2 sources will not be the same. Yeah. So imagine that we have an object that we want to see, and it has a specific color. What happened exactly is that the light source falls on an object. This object will absorb all colors and will reflect only its own color. This is the general rule. However, we have exceptions for 2 colors, which are the black and white. For the white color, the white does not absorb any component of the lighting spectrum, but will reflect all. On the same time, the black color will absorb all and it will not reflect any color, or it will not reflect any wavelengths. Thus, we need, I mean, you see it now, we mentioned wavelength or wave many times, so we need to understand what is wave. Wave is a disturbance that transfer energy through a medium or space. If you look at this graph, you will see like we will have something similar to sinusoidal waveform, where we have an amplitude, which is represented by the A character here, and the A character can change, vary. We have also lambda, or what is called the wavelength. We have a frequency and we have the speed of light. The wavelength and the frequency, they are correlated together in the below formula. The frequency equals the speed of light, which is almost 3.10 to the power 8 meter per second, divided by the wavelength. So what is the effect of the wavelength on the color itself? If we will change the color, if we will change the wavelength, the color will change. Or we might be achieving to an area where we cannot see it as a human being. So for instance, if we have short wavelength like the wave here, we see that we have violet color. And if we start increasing the wavelength, if we start extending it, the color will change to blue, green, till we will reach to the red and the high wavelengths, or in the long wavelengths. Okay, so changing the wavelength will change the physical property of the wave. This might include, of course, the color change, or even the ability to penetrate objects. Like if we have radio, for example, radio is also a wave, and we cannot see it in our eyes. However, it can travel for a very long distance because it has a very long wavelength. On the other hand, gamma rays, if you can see the graph here on the left side, is a very short wavelength, and it will not be able to travel for long distance, but it has a very strong ability to penetrate objects. And that's why gamma rays are used heavily in medical treatment, as those rays are able to penetrate tissues of the human being, and they are used to kill bacteria and maybe cancer cells in some cases. From all of those spectrum, we have spectrum starting from 10 to the power minus 15 meter up to kilometers. We as a human being will not be able to see it all. We will just see a very narrow area in the spectrum, starting from 380 nanometers, and the maximum we can reach to is 780 nanometers. If you look again at the colors, as much as you are increasing the wavelength, as much as the color is changing. And the color that you see here is very similar to the rainbow colors, the seven colors of the rainbow. If you look again here, there is no white color in between. And why is that? Because the white color is mixture between two saturated colors. Those colors that is independent are called saturated colors. Okay. To be able also to understand how vision is happening, we are also looking at the eye anatomy. We find that there is two sensors integrated inside the eyes, which is the rods and the cones. They are specialized cells. They are found on area called the retina and fovea, and they are responsible about our vision. Those cells perform different functions, making it is possible to us to see and to have a clear vision during the day and the night. What they do, those sensors, they convert vision or they convert light into electrical message that will pass through the optical nerve to the brain, and then the brain will process it, and then we will be able to see. The rods and the cones are named for their shape. So the rods will look like the rod, and the cones will look like the cone. The cones are concentrated on the fovea here, while the rods are concentrated in the retina. Inside the human eye, we will have a lot of the rods and the cone. Some study mentioned that we have almost 130 million rods, and we will have also 7 million cones, which is responsible for our vision. Those two sensors, the rods and the cones, are similar in the fact that they will help us to see. However, every one of them will have different functionalities. The rods, which are responsible about our vision, they are also responsible about sensing motion. They cannot transmit sharp images or perceive final details, and they are not sensitive and cannot perceive colors. On the other hand, cones are responsible for fine detail vision, and they are responsible also for color perceptions. And that's why we will not be able to see the same colors all over the day. There will be always relation between the light level and our ability to see colors. Why is that? It is because rods are active and they are responsible about night vision when the light level is very low, less than 0.001 candela per meter square. And in that limit, if we were under these circumstances, we will be able to see black and white objects, or the same object, we can see it without color in black and white. We call this type of vision as scotopic vision. Cones, on the other hand, are responsible for daylight, and they will be active completely once the light level is above 3 candela per meter square. The type of vision that they are performing is called photopic vision. For the cones, we have 3 types. We have the red, the green, and the blue. So what we see here, we have very low levels. If we are under it, then we are in scotopic vision, and we have 3 candela per meter square, and if we are on top of it or above it, we call it photopic vision. The area in between, if the light levels is between 0.001 candela per meter square and up to 3 candela per meter square, we will have what's called mesopic vision, where we have combination between rods and cones. We will not be able to see colors in the same way if we are in the photopic vision, but we will see some colors. And we will not also be not sensitive to colors like if we are in the scotopic vision area under the 0.01 candela per meter square. We mentioned earlier that the human eye sensitivity is not the same for all colors. And this is very clear in the graph on the left-hand side. We can see that the cones, which is the sensor responsible about the day vision, for the photopic vision, they are sensitive for the 555 nanometers. If the light level is falling and we will be somewhere under the 0.001 candela per meter square, we are shifting for the scotopic vision, and the eye sensitivity will shift from the green yellowish to the green bluish area. We need to keep this in mind because some of the authorities, they are taking advantage of this fact that the eye sensitivity is going toward bluish at night or when the light level is very low. And we will compare the spectral distribution between 2 lighting sources, the high pressure sodium, the one on the above, and the cool white LED. If you will put both spectrum in top of each other, we will find that in the high wavelengths, the high pressure sodium is covering most of the colors, especially on the green and yellowish, but it does not have a lot of blue components. While LED will have, especially the cool white colors, will have a high portion coming on the bluish color. And as the eye sensitivity during the night is shifting toward the bluish, we expect that at the same light level at night between high pressure sodium and the cool white LED, the eye will be more sensitive toward the LED. And hence some of the authorities like the PSEN 5489, which was introduced in 2013, they identified what is called SP ratio, scotopic photopic ratio, in the table above. And we see that for every light source, we will have different ratio. For incandescent, it's 1.36. Fluorescent warm colors is also 1.36, but fluorescent 5000 Kelvin, which is cooler, the SP ratio will be higher to 1.97. For high pressure sodium, we see that the value is very low, it's 0.65. And for the LED, if we are speaking about the cool white colors, we are seeing that the SP ratio is very high, 2.18. On the same standard, they have allowed designers or owners of street to reduce the light level if they are using a light source that has a high blue contents. For example, here, if you are using normal bulb without considering the SP ratio, the light level required is 15 lux. If you will be using a light source with the SP ratio of 1.2, you can go from 15 to 13.4. And if you have a light source which has higher content of blue colors, you can go even to 12.13. And hence, they will be doing saving, first of all, by shifting from conventional light source like the high pressure sodium to LED. And the other saving that they will have, that they are allowed to reduce the light level and hence generate more savings. This is an example of how vision is different according to the light level. In the first photo on the top, this is the day vision when we have photopic vision, whereas the green, whereas the red color is very clear. In the second photo here is the same area, the same photo were taken when the light level reduced less than 3 candela in the mesopic vision area, and we see that the red is not as clear as the red on the above photo, and also the green start to be more obvious. And finally, in the night vision, scotopic vision, where the light level is very low, less than 0.001, we see that we are not able to distinguish colors. We can see things only in white and the black color. Okay. In the next sector, we will be discussing 3 different concepts that we see almost every day in our work, which are the color temperature, the CCT, correlated color temperature, the CRI, which is the color rendering index or the color rendering, and the spectral power distribution, which is very connected to both of the CCT and the CRI. Going back to the same electromagnetic wave, and we again concentrate about the visible area, we see that we have colors similar to the color of the component of the rainbow, and those colors are called to be saturated. Saturated means that if we allow the light to go through prism and we take any color of those and we will allow it again to go through prism, we will not be able to see any new component. It will be that color only. So what happened? There is something called the CIE chromaticity diagram, where they took the same colors, which is the color above here from 380 nanometer up to 700 or 780 nanometers. They took it and they draw it in the graph with the X and the Y coordination. So this, they identify that this chromatic diagram is a graph that's showing all possible colors. Any color that will come to our mind will be in this graph. Each color here, wherever you want to put your pointer, is identified or is defined by a pair of numerical coordinates, which we call the chromaticity coordinates. So we can represent, for example, the 4000 Kelvin, or this white with x equals 0.4 and y equals 0.4. So every time we will put in any software in any area, you will find the x and y coordinate is 0.4, 0.4. It means that we are referring for exactly 100% the same color. We can also see here the points around the curve are the saturated one that we mentioned earlier, and they are the component of the rainbow. Okay. We got here the same curve in two different graphs. And if we look now to the right side hand, the right one, we see that if we draw a line between 2 points, this will show us the color that can be produced by mixing those colors. So from A to B, if you want to achieve any light in this line, we need to mix the 575 nanometer with the 475 nanometer. The exact area, point A, it means maybe 50% of this and 50% of this. If we are going more toward point A, the concentration of point A will be higher, so the color will be closer to the 575 nanometer. And if we are going toward B, we are going closer to the 475 nanometer. So different lines, different points in this line represent different mixture between the two colors. Then any color, if we are looking here, any color inside this diagram can be made in many different ways. So the point T here, it can be made by mixing C with D, and also it can be made by fixing G and F, and can be made by mixing J and H. At the end, you will have the same appearance in color, but of course, the quality will not be the same, or the quality of objects under this color will not be the same. Okay. So any color in this point can be met by many ways, by mixing many ways. The only exception that we have is the color which is in the edge of the curve, which is a saturated color, because it is only one color and it's not mixed between any other colors. Okay. What happened if we extend the mixture instead of 2 points to 3 points? We will reach to the graph to the left side. If we mix color from 3 different colors, we can produce any color which is in between. So if I have the point, let's call this A, B, and C, and I want to produce D, which is here, I can just make it by changing the component. I mean, how much we are adding from a specific color and how much we are not adding from the different colors. That's why if you see normally that in illumination segment, even in TV industry, they are selecting 3 colors, which are red, and if you see red is coming on the corner here, green, which is on top, and the blue. By doing this, you are maximizing the area that we can cover. Unfortunately, it is not always easy and cheap to produce, especially for TV industry. It is not easy and cheap to produce the RGB colors from the saturated area, and then you will end up with something similar to the triangle that you can see here. And that's why we see some differences or variance between two TV suppliers in the quality of the colors that they are producing, because they are not using exactly the same points, the same R and G and B. Maybe one guy will start here, the other company will start here or on top. Yeah. Okay. Inside the big area of the CIE curve or CIE chromaticity diagram, we have a specific line dedicated for white area. You can see the white area is here, and we can see on this graph that there is something called Blanken locus, which is the area where we find the white light. The Blanken locus is identified or is defined as the curve formed on the CIE chromaticity diagram by plotting the chromaticity of a black body at various temperatures. Once we are representing a specific degree of color, and we will come to speak about it, a white color with 3000 Kelvin or a white color with 4000 Kelvin, we are representing an area, not a single point, but an area surrounding it, because it will be also, again, very difficult in the process of producing the color, the LEDs. It will be very difficult or impossible to have 1 million LED chip produced with 100% the exact temperature in degrees. Always we have acceptance or acceptable variation from a reference point. Okay. We see here that we have the letter K, which is representing Kelvin, and we all know that Kelvin is something related to temperature. So if we are speaking 2007 Kelvin, we are speaking about almost 2700 minus 273 to get something around 2330 degrees Celsius. And of course, we are not expecting that we have really a very high temperature inside the bulb. If we bring a thermocouple and we will go for 3000 Kelvin lamp, we will not find 3000 Kelvin temperature. But what we will find that if we bring perfect black body and we put it inside an oven and we start heating this body for different temperatures, we see that if we are heating it up to 900 Kelvin, we will have a red color or reddish color. And then if we start to increase it a lot up to 6000 or 5500 Kelvin, we will find bluish color. For 1750, we have yellowish. For 3200, it's white yellowish. So from here, they decided that they are looking at the light source color, and they are comparing or they are referring it to the color of the black body when it is heated. So in simple words, if we have a light source with 4000 Kelvin, it means that this light source will look exactly similar to the black body when it is heated to the 4000 Kelvin. And again, once we say 3000 Kelvin, normally it is not 3000 exactly, but always we will have a plus minus deviation. And how acceptable is this deviation? This all will be identified by the macadam or macadam ellipse. So what is macadam ellipse? So let's look, macadam ellipse, we can separate the two words. We will have a word called macadam, which is a name, and we have the ellipse. So who's macadam? MacAdam is an American color scientist who made important contribution in the field of colorimetry, color discrimination, and color photography. He was working for Kodak, and he was doing a lot of experiments in color and color discrimination, the ability of a human being to distinguish between different colors. MacAdam experiment was relying on a visual observation of what is called just noticeable color difference, JND. So he will bring a sample of people, maybe 50, maybe 100, and he will give them two colors, and he will ask them to identify if there is a difference between them. Of course, if the colors are very close, nobody will notice a difference, and if the colors are totally different, everybody will notice the difference. But in between, if the colors are very close to each other, people will not have the same capability of distinguishing colors. I might be able to, or somebody might be able to see a very small difference in color degree, and other people will not. So what he did, he identified that there is something called JND, or just noticeable color difference, if 50% of the sample that he brought will be able to distinguish, and 50 will not be able to distinguish between the two colors. He brought his finding just where will be the edge of the 50% of people will be able to distinguish colors, and where 50 people will not be able. And he plotted those on the chromaticity diagram, and he found that always the shape of the graph that was plotted is similar to an ellipse. And that's why we start to say macadam to his name and ellipse, because within a specific ellipse, maybe we will speak about one step later, but 50% of people will not be able to distinguish the color difference inside the ellipse itself. Of course, if you look here, all of us will be able to distinguish of the ellipse that we see, because this ellipse is magnified 10 times just for us to be able to see and to understand the ellipse itself. In real life, it will be much smaller. So it is easier to distinguish differences in color if you look here on the warmer side more than the cooler white. What macadam did exactly, he found that the size and orientation of those ellipses is varying depending upon the location on the CIE chromaticity diagram or the color space diagram. The zones were observed to be largest in the green area. If you see here, this is very large compared in the red or the violet area. What does this mean? It means that it is much more difficult to distinguish between color differences once we are in the green area compared to the red area. It's easier for us to see that there is difference between this color and this color in the reddish area. In the chromaticity coordinates of a set of LEDs will fall within one step, most people will fail to see the difference in color. So if we have in specification or somewhere says that one step macadam ellipse, it means that the majority of a human being will not be able to distinguish between two of those colors, even if you are putting them next to each other. Again, we said that in two-step macadam ellipse, more people will start to see some color differences. Maybe not everybody, but if we are speaking earlier about 50%, maybe now we are speaking about 60%. I don't have the figures, but I mean, this is the logic behind it. For one-step macadam ellipse, maybe 50% will be able to see difference, and two-step maybe 60, and three-step maybe 70, etc. Till you will reach to the moment where everybody maybe at 7 macadam ellipse will be able to see differences between two LEDs if you will put them next to each other. Two-step macadam ellipse is better than three-step macadam ellipse, but it's not always required. Different industry will require different macadam ellipse or different color differences. For instance, if we are speaking about cove lighting, where we have strip lights that will be installed very close to the ceiling, few centimeters. If we have a very big difference or noticeable difference between the LED colors on the LED strip itself, it will be very obvious for everybody who's passing to notice a difference, because the distance between the strip and where the light will be projected is very small. There will be no enough space that color will mix. Then you can see on the wall itself or the ceiling that the color is not consistent. And that's why people are recommending very low step macadam ellipse for strip lights. At the same time, an application like street lighting, where our luminaires normally, especially on road, will be installed in very high poles. We can reach, of course, up to 20 or maybe 30 in some cases. Typically will be around 8 to 10 to 12 meters. The distance is enough for color to mix. So normally, whatever the macadam ellipse level is inside the luminaire, you will not be able to notice this in the ground. However, if there is big difference between the colors inside the luminaire itself, anybody can notice if he will be looking directly to the luminaire itself. So normally, once we are speaking about street lighting, the requirements will be maximum 4 to 5 macadam ellipse. Now, to understand what is the value that we have to consider for macadam ellipse, we have to understand that the ellipse itself is not the same everywhere. the size of the ellipse or the border of the ellipse is not the same everywhere. So if we are going here, we see that this ellipse is not like the same dimension of this ellipse. So I cannot always tell one step ellipse means 15 or 20 or 50 Kelvin, because it will really depend on the location on the CIE chromaticity diagram. If we are looking at the graph here on the left side hand, we will find a table of the 7-step macadam ellipse at different color temperatures at 2700 Kelvin, 3000 Kelvin, 3500, up to 6500 Kelvin. We see that to be within the 7-step macadam ellipse, we are allowed to go from 2725 plus minus 145. So here the delta is 145 at 2700. However, if we are going to 6500, the delta is increasing from 145 to 510. Why is that? Because it will be much more difficult for us to distinguish colors at the cool white, and then it is the ellipse size which will be greater. This is not the only parameter or criteria that will identify the macadam. There is also something called DUV, which I will show in the next slide. But keep in mind that there is also figure or maximum DUV, which is allowed within the same macadam ellipse. On the other side, if we are looking on the graph here, it is showing the 3000 Kelvin. So here we showed 7-step macadam ellipse at different color temperatures, and in this graph we are showing the same color temperature of 3000, but one time with one macadam ellipse, 2, 4, and 8, and we see that at 1 is 30 Kelvin. If we bring instead of 3000, we put 4000. Definitely we'll have maybe 35 or 40, something a little bit more. The same for the 2-step macadam ellipse is 60K, 4-step macadam ellipse is 100K, and 7 to 8 macadam ellipse is 170K at 3000 Kelvin, which is in line with what we see here. We will have also limitation on the DUV. So what is DUV? To understand DUV, we have to understand something, that the chromaticity diagram or the CIE chromaticity diagram that we showed is not that simple. It's not a 2-dimension graph. It is very complicated graph, but what we are showing or what everybody is using is the simplified version of it. We have the X and Y curve, but also there is something called U and V curve, which is a little bit different in values. And here, if we are going to the color temperature itself, so for example, if you are looking at the 3000 Kelvin, everything which is on this line is considered to be 3000 Kelvin. However, the optimal color that we want to see is once we are exactly on the black and locus line here. So as much as we are deviating in a plus or in minus, macadam ellipse will also identify the limit that we have here. If you saw here, you are allowed to deviate for 0.006 plus and minus. And here, you are allowed plus and minus 2 divided by 1000, which is 0.02. So what's the effect of that? If you are looking at the picture here, the item or the light on the right side and the light on the left side. If you look initially at them, you will tell that those are totally different colors. They are not similar. But if you do a test in the lab, you will find that they are very similar. This is a 3265, 3285. So the difference is almost 50, less than 30. Sorry. Less than 30. So ideally they should be with 1-step macadam, and majority of people will not be able to distinguish. But due to the fact that we have DUV plus and DUV minus, it seems that they are not in the same macadam ellipse. It seems that there's something on the plus and the other one and minus. Color rendering. Color rendering is also an important terminology where we are facing every day in our lifetime. I know that everybody understands what is color rendering, but I'm trying to explain it in a different way. If we are looking at the photo here, and if we are compare the colors of the two carpets, we see totally different colors. If you are looking here at the green, and the sea green is different. If you look at this color, and the brown here is different. However, in real life, the photos were taken for the same item, for the same mat, for the same carpet. The only difference between them that they are under two different light sources. We can see this not only in our daily work, but also in our daily life. Imagine that you want to buy some clothes and you like the color from the shop. You wanted to for example, to buy red or a green t-shirt, and you decided to select it because it has very nice color. You bought it, and once you go to home, you open the package, and you found that it looks totally different. Of course, this does not mean that the seller provided you something else or they cheated, but it's because the light source in the shop, it is totally different than what you have at home. So how this is happening? If you look at this graph, and for this apple, if you'll take it outside under the natural white light from the sun, we see that the natural light will have all the components of the rainbow, all the wavelengths and the visible spectrum. So all the light will fall on the apple. As the apple is red color, it will absorb all colors and it will reflect its own color. So this is how we are seeing this as red. If we will take the same apple and we will go to a poor CRI or poor color rendering lighting source, all the colors of the light source will fall again. This apple will absorb all colors, and as it does not have its own color, the red one, it will reflect the closest one. So you will see it not red, maybe dark red, or maybe, I don't know, this is orange or some different color. Here an example, if we have two light sources where we have for both them, or the sunlight source and the other artificial light source, where we have very good rendering, and we see here as the light itself will have the red component, it will be easy for us to see the red color. Okay, so this is very nice, but we need to understand also why the CRI is considered to be a number. The maximum number that we can reach is 1 or 100, but what's the relation between this and that? So what they are doing in lab, if they want to identify what is the color rendering of a certain lighting source, they test the light source in comparison with different light source using 15 different test colors. Of course, the other light source should be ideal. Ideally, it should be the sun. Maybe it's not. If it is not practical, they will use some other light source which has very high rendering, like the incandescent light. So all of those 15 colors will be compared between the light source that we want to test with a reference light source. The evaluation bandwidth is between a maximum of plus 100 and it can go as bad as minus 60. The more accurately the light test or the color is reproduced, the higher or better the color rendering value. Then after that, they will add, or they will do the mean value of the first 8 colors, and they will give you the color rendering index, which is 70, 80, 90 itself. For some other application where it's also very important to have the red, yellow, and some of the other color, they are going from R9 on the graph, if you see here, up to R15, and they are giving values for those. What we see so far, that the spectral distribution is very important. Why it's very important? Because as much as the light will have or will cover the visible light spectrum, as much as the color will have, or the light will have higher quality, and the object will render and look better under it. In the example here, we see the daylight, how does the spectrum distribution looks, then the incandescent, and finally for a specific poor color rendering fluorescent lamp. We are comparing here between two lighting sources. Both of them will have the same color temperature, which is cool white, 6,184 Kelvin. For a fluorescent lamp, where we see in the red color here the color rendering for it. On the same time, LED lamp, where we have the spectral distribution here. What we will do, we will be comparing this fruit basket under both the lights. So on the right side, we will have the blue spectrum here, and we see that we are covering almost all the colors. We have violet, we have blue, we have green, we have yellow, we have orange, we have red. So under this light source, where we have very high color rendering index, we are expecting that the color will look natural, and we can see this. Look at the melon here. It is red color because we have a lot of red. The orange, it looks orange because also we have orange. Green, we have green. Again, orange and yellow. Yellow, we have yellow, and we have also orange. On the other hand, if we are looking on the basket or the same basket after putting it under the fluorescent with the poor color rendering, we will see that the fluorescent here does not have red color. We have some degree of red, but it is not the real red. So what will happen in real life? You look at this and you compare this. Because this light source of fluorescent does not have the red color, you will not be able to see the red colors of the melon here. Orange, it will not have orange, and look at the orange here and then compare it with here. Here they have yellow, so the color of the orange will shift to yellow, and I'm not able to distinguish if this is orange or yellow or lemon. Green for the grapes and I don't know, the kiwi, they are almost the same if you notice. Why? Because we have high green component on the light source spectrum. Yeah. So I hope that this was clear for understanding in different way how to look at the color rendering and the color temperature. Of course, there is a relation also. I mean, here we can see that by initially looking at the spectral distribution, you'll be able to identify that this will be high or low color rendering, and also after time maybe you'll be able also to expect that this will be warm or cool or neutral white. Finally, we will go also for the four fundamental photometrical units that we are usually using, which is the luminous flux, luminous intensity, illuminance, and luminance. And we will explain each one in very simple way in one slide. So just let's concentrate at the photo that we see here. We see that we have a lighting source. We see that we have the ground, and we have some light rays coming down and reflected. So luminous flux is identified as the quantity of the energy of light emitted per second in all directions. I will forget about the definition and I will think only about the total amount of light. So if this is the light source and I want to see what is the luminous flux, I will just think about the total amount of light which is emitted from the light source in all dimension. Does not be specifically going in one direction, in all direction. This is called the luminous flux. Of course, the symbol of the luminous flux is phi, and the unit used is lumen. If you look at the datasheet of any light source, you will find how many lumens it's producing. Yeah, maybe this is a typical table which shows normally approximately what will be the values for luminous flux of different light sources. We see that if we are looking at the bicycle headlamp, we have something around 30 lumens. If we go to high pressure sodium for 100 watt, we will have something around 105. For metal halide, we might have for 2000 watt, almost 220,000 lumens. And for neutral white, for one LED, we can have 160 earlier. And right now, we are almost achieving 185 in some of the LED chips. That to be able to compare those together, you see there's a big variety of those. So the ideal way is to divide the luminous flux by the wattage. to get what is called efficacy, which is lumen per watt. And hence, once we have the lumen per watt, it will be easier for us to compare a light source with the other. Okay, it's not 100% correct comparison, but it will only give us an idea, because after that there will be the efficiency of the lenses, etc., where we will be covering on the luminary structure later. But the efficacy will give us an indication about how efficient the light source or not. And most of the specification nowadays will be requiring a minimum value of the lumen per watt. So looking here for the bicycle headlamp, we will have 10 lumen per watt. And if we go to the low pressure sodium, it is the highest efficacy ever, where we are able to hit almost 200 lumen per watt. For the LED, we are almost, depending about the driving current, and we'll be speaking in details about it on the next webinars, specifically the webinar speaking about the luminary structure. We can achieve at 350 milliampere up to 185 lumen per watt. How to measure it? We have a dedicated equipment called sphere, Alpert sphere, where we are putting the light source inside it. We will close it. And then the light will be emitted from the light source and will be reflected everywhere, and then gathered in a sensor where it will measure exactly how many lumens were emitted from the light source. The second unit, or the photometrical unit, is the luminous intensity. We are looking again at the same graph that we saw earlier. We identify luminous intensity as luminous intensity is the ability to emit light into a given direction. So we have a direction here, or we can also look at it as luminous flux that is radiated by the light source in a given direction with the unit of spatial angle. So for us, we will also forget about the definition here. We will think about the luminous intensity, about the amount of light emitted from the light source in a specific direction. So if we have flux, luminous flux going in all directions, the luminous intensity is the amount of light going in a specific direction. The flux, luminous flux unit is lumen, and the luminous intensity unit is the candela. Measurement of the luminous intensity is a little bit more complicated. We will need bigger space to test it. So what we are doing, we have something called goniometer, where we are mainly using it to do the LM79 testing, but it will allow us to measure the candela values of the light source. So we will have the light source inside the lab, and we will have a sensor that is rotating around the light source, gathering the information about the candela value in each direction. Illuminance, on the same graph, the illuminance is defined as the amount of light that covers the surface. So we are going to the surface, and we care here about the amount of light which is falling. So amount of light emitted in all direction, amount of light which is falling in a specific direction, and the amount of light which is falling on the direction, on an area. We need to highlight here that the illuminance value does not depend about the surface. I mean, if we have asphalt, or if we have mirror, or if we have any color of the material, we will have the same illuminance value, because it depends about two factors only, which is the light source flux and the candela value. It does not depend here. Maybe in some application like indoor, it will depend about the walls, because there will be reflection from there to gather here. But in real life, in open space, there is no relation with any surface. In this example, we can see some of the illuminance recommendation in some areas, like in country roads. We will need very low candela values, very low illuminance values from 5 to 10. In highways, 15 to 30, and roundabout, because it's a conflict area, and we will be covering this in the CIE standard next webinar. It will be a little bit higher with 30 to 40. In football field, it can go up to 800. In offices, we will have a typical value between 300 to 500. In tunnel entrance, and it will be covered in details on the CIE 88 webinar, we will have something between 2000 and 3000 Kelvin, 2000 and 3000 luxes. And finally, in a sunny day, we can get up to 100,000 luxes. We just need to mention that we are showing here the lux values. However, we will, for the highways and for the other parameter tunnel. However, for those two line for highway and tunnel, we are measuring candela per meter square, where we will be discussing in details in the next webinars. Unit of measurement, we will have very simple unit. We might even use our mobiles. Here, there's a question about the accuracy of that, but we can have a sensor and then it will measure the amount of light falling in that surface. You see that it's very simple, and then we normally, for street lighting, we will have some device like this, just in case if we have RAM, to make sure that the slope will be balanced, and then the sensor will be horizontal or parallel to the sea level. Finally, luminance, which is which is defined as the luminous intensity emitted by the surface area. In the graph here, again, we will forget about the definition, and we will think about the amount of light which is reflected from an area to other area. So here it's the L, which is candela per meter square. In this example, we will see that there's a lot of parameter. It's not like lux. Lux does not depend about the surface, but here, of course, the surface is very important and critical part. If we have a black surface, we will have totally different level of luminance if we compare to what we will have if we have mirror. And also the position of the observer will be different. If we are looking from this angle, we will have totally different than if we are looking from different space from here, for instance. This again, also we will be speaking about in details how what is the international standard identifying the exact point where we have to look once we are measuring the luminance values. This is typical values for luminance in different surfaces. In a street, we can go sometimes to 2 candela per meter square. The moon will be having 2,500 candela per meter square. The surface of the sun will be 2 billion candela per meter square. To measure the candela per meter square, we will have a device called luminance meter, and of course, in the CIE 140 and 115, we will explain exactly how to identify the location where it has to be kept to do the measurement of candela per meter square. Okay, I think that's all. The only thing that on this slide I will put the four terminology that we discussed on the same graph. So looking at the light source, or the light going in all direction, is the luminous flux. Looking at this direction, or the light going from light source in a specific direction, is called luminous intensity. Illuminance is the amount of light falling on a specific surface, and which is in lux, and luminance, which is in candela per meter square, is the amount of light which is reflected from the surface in a specific direction. And thank you all for listening. I don't know, Iris, if we have any questions.